Today, I want to show you something that completely changes the way you see transport phenomena. Heat transfer, mass transfer, and momentum transfer are not three unrelated topics. They are actually the same physical mechanism, just appearing in three different forms. In every case, we're going to have a flux that is proportional to a gradient multiplied by a proportionality constant that becomes a diffusivity, which has units of meters squared per second. Now let's talk about this term, flux. What is flux? Flux is simply the amount of something moving over a unit area per time. So the key thing to remember here is per area per time. And as I said before, we are going to be discussing momentum, mass, and heat and their relationship. Heat flux can be described using the term Q with these two hash marks above it. Heat flux is equal to the negative thermal conductivity multiplied by a change in temperature with respect to position. And we call this equation Fourier's law. The unit of heat flux is joules per meter squared second. Again, per area per time. The unit of our temperature gradient is Kelvin over meters. Therefore, the unit of our thermal conductivity must be joules per meter Kelvin second. Now you might be asking yourself, why is there this negative in front of our thermal conductivity? I'm going to explain that to you using a temperature profile. Over on the y-axis, we're going to have this representing our temperatures, and on the x-axis, this is going to represent our positions. So I'm going to denote this at the origin at position x is equal to 0, and over here as position x is equal to L, some length. Now let's say we have this object. And this object at differing positions has different temperatures. At one position, some position x, the object is at 100 degrees Celsius, while at a different position, it is at 200 degrees Celsius. This relationship is linear. And we also can see that the direction of increasing x values goes from left to right. We know that heat travels from higher temperatures to lower temperatures. Therefore, our heat is going to be traveling in the opposite direction than that of position. Because those two directions are opposite to each other, we need to denote that using a negative value in front of our thermal conductivity. Now I want to start talking about momentum, and to do so, I'm going to write out our equation for shear stress. Shear stress is tau, which is equal to viscosity multiplied by shear rate, sigma. Tau can be written as force divided by area, which is equal to our viscosity multiplied by our shear rate, which is the change in velocity perpendicular to the direction of flow. We saw this in velocity profiles we worked with in Transport 1. Now in both of these cases, we can see that we are going to have something which is equal to a gradient multiplied by a proportionality constant. Now I want to introduce mass flux. Mass flux can be written as J in units of mole per meter squared second, again, area, time, which is equal to a diffusion coefficient D multiplied by a change in concentration, which we'll put as Ca, with respect to position. Concentration has units of moles per meter cubed over our change in position in meters gets us units of moles per meter to the fourth power. Seeing this, we know that our diffusion coefficient must have units of meters squared per second. Going back to our shear stress equation, if we want to take this change in velocity perpendicular to the direction of flow and multiply it by density, we will have d rho dx over dy. Thinking about units here, density has units of kilogram per meter cubed, and velocity has units of meters per second. Multiplying this, we are going to get kilogram meter per meter cubed second. Kilogram meter per second is known as the units of momentum. Dividing by our volume and our change in y, we get kilogram per meter cubed second, which is our momentum concentration. If we multiplied our change in velocity perpendicular to the flow by rho, we must then divide our viscosity by rho. Doing that, we get a term of kinematic viscosity. Now let's discuss the units for kinematic viscosity. The units for force over area are kilogram per meter second squared. We know our units for momentum concentration as kilogram per meter cubed second. Therefore, the unit of our kinematic viscosity must be meters squared per second. Now, taking a look at our heat flux equation again, we can see that this is not really a concentration like our other examples. So let's write that down here. Heat flux is equal to the negative thermal conductivity multiplied by the change in temperature with respect to position. If we want to relate our temperature term to be in terms of energy, we need to multiply temperature by the heat capacity. Temperature is in units of Kelvin. Heat capacity is in units of joules per kilogram Kelvin. Multiplying this across, we see that our kelvins cancel and we're left with units of joules per kilogram. Now we're taking a derivative with respect to position. So because of that, we need to relate our kilograms to spatial units. To do so, we are going to multiply this by the density rho, which has units of kilogram per meter cubed. Multiplying this across, our kilograms cancel, and we are now in units of joules per meter cubed, or energy per volume. So multiplying this, we're going to have the derivative rho CT, all with respect to x. This term becomes our energy concentration. Just like we did before with shear stress and our viscosity, because we multiplied our temperature by density, and heat capacity, we need to divide our thermal conductivity by density and heat capacity. As we said before, the units of thermal conductivity are joules per meter Kelvin second. Multiplying by the reciprocal of density and heat capacity, we're going to have this multiplied by meter cubed per kilogram multiplied by kilogram Kelvin over joules. We can see that our joules cancel, our kelvins cancel, and our kilograms cancel. Meter cubed over meter is meter squared over second. This thermal conductivity divided by rho C term is thermal diffusivity. Which we will denote as alpha. Now we can see that the difference between thermal conductivity and thermal diffusivity is rho C, or the volumetric heat capacity. So to take an example of this to further describe their differences, I want us to imagine that we have two rods. Both of them have the same thermal conductivity value K, but they have different metals. One has a very high volumetric heat capacity while the other has a very low volumetric heat capacity. If you take the rod that has a very high volumetric heat capacity and you stick it into something that's really hot, as heat conducts through the rod, it takes more heat transfer for that high temperature to reach your hand on the other side. Whereas if you have a low volumetric heat capacity, it doesn't take near as long for that hot temperature to reach your hand. Therefore, you will get burned quicker. So the thermal diffusivity is the rate at which temperature differences diffuse, while thermal conductivity is the way in which heat is transported through conduction. So as we can see, in each case, mass, momentum, and heat, we have a concentration gradient multiplied by a diffusivity with units of meters squared per second.